students, staff, both teaching and non-teaching. And of course, a very special welcome to our speakers today, Dr. Tarun Menon and Dr. Shitabra Sinha, who are here. And then, of course, very shortly, we'll have Dr. Srinivasan Ramani joining us, okay? 25 years, 26 years ago, in fact, when we, people were looking at the syllabus for the Asian College of Journalism, one of the things that they thought was that we should absolutely have a science elective, science writing, a kind of a writing course on science elective, which was as important as the politics elective or the critical international issues or sports or any other elective. And I'm happy to say that over the past 26 years, there's not been a single year when we haven't had the elective. One of the reasons for this insistence on a science and technology elective was that 26 years ago, it was practically non-existent. This idea, science journalism in India. You had a couple of dedicated journals concerning, something like Nature or other journals which were dedicated to science, but those were written by scientists. Ordinary people like you and me, journalists, who needed to get involved in science writing, there were very few, hardly anything at all. Over the past 26 years, very happy to say that we now can be proud of the fact that many of our alumni are doing excellent work in science journalism, both in India and abroad. But there are many pitfalls, when it comes to science journalism, that, in fact, our own alumni have talked about it. One of the pitfalls really is to look at it as any other political story and think in terms of providing a balance for a science story. It doesn't work that way. In science, for instance, in climate change, you are not going to find people who are for climate change and those who are against it, because there is a scientific consensus that there is climate change. And suddenly you're not, all the people like Mr. Donald Trump, for example, they are not the other side, so to speak. They are non or anti-science, really. The other pitfalls that people talk about are, and scientists will tell science journalists that they should not commit sins of commission or sins of omission. In other words, due diligence, and that's important. Every year, as I was just talking to this year we have Dr. Shitabra Sinha, who will be taking the science elective. He took it last year. That was his first year, and this is the second year for him. Through the past 26 years, it's also true that we've had several scientists, really, who have taken this elective, offered the elective. And except for one science journalist who presented it, in most other cases, there were surprisingly physicists who were offering this elective. So right now, let me also inform you that we have in the Asian College of Journalism, we also have a climate change hub. It's something that we are very serious about, and we are establishing it. The other hub that we are planning is an AI hub that Mr. Sashi Kumar is very keen to establish in Asian College of Journalism. Interestingly, our first speaker will be speaking on the subject of AI, and the topic is digital wisdom, navigating the AI landscape. This is Dr. Tarun Menon, who is an associate professor at the School of Humanities and Social Sciences in Azim Premji University. And he teaches in the philosophy and PPE, I suppose that's philosophy, politics, economics, programs. He works on the philosophy of science, especially on questions about the nature of explanation in the natural and social sciences and the role scientific institutions should play in policy making. He is currently working on whether the use of artificial intelligence in scientific research sacrifices scientific understanding in order to achieve predictive success. Dr. Tarun Menon, we are very happy to have you here, and we look forward to listening to your lecture. And I suppose you'll speak for 45 minutes and probably have half an hour for, 15 minutes for questions and answers. That will be followed by a coffee break, and then we move on to the next speaker. Thank you, Tarun.
Thanks a lot, Nalini. So, as the introduction suggested, my interest these days, or one of my interests, is the way artificial intelligence is used in science. I generally am interested in how science is done, the process through which science is done, and increasingly, a lot of science is now being assisted by artificial intelligence tools. But what I want to talk about here today is not so much the use of artificial intelligence specifically in the context of science, but give a kind of general idea of how best to think about the artificial intelligence tools that are available to us today. And the reason is that I think there are some misconceptions that circulate in the popular literature about how exactly these tools function, what their capabilities are. These can both be a kind of overhype of these tools, a kind of, recently you had Elon Musk saying that in, I don't know, a few years, 10 years, 20 years, something like that, AI will outperform human beings in every endeavor that we participate in. You've had people saying that all science will be done by AI in the near future, 20 to 30 years from now. On the other hand, you also have, I think, an opposite tendency, which is a kind of underplaying of the significance of the technology. And this often has to do with arguments that, so there's this phrase that comes from the linguist Emily Bender, that artificial intelligence models, the kinds of models we are acquainted with now on an almost day-to-day basis, like ChatGPT, Claude, Grok, and so on, that these are mere stochastic parrots. This is a term that has become quite familiar to a lot of people. And the idea there is, so the metaphor of stochastic parrots is supposed to indicate the fact that, look, all these systems are doing are kind of blindly mimicking or imitating the training data they're trained on, human speech. There's no real sense of understanding or thought embodied in these systems. And the reason it's not exactly like a parrot will, I guess, repeat what you say word for word, but these models are stochastic. Stochastic is a word indicating some kind of unpredictability, chance, randomness, that because there's some degree of like unpredictability built into the output, you end up getting something that looks slightly more convincingly like thought, but it's still not genuinely thought, right? And I think that is also a mistaken view of what these AI systems are capable of. In fact, look, I don't want to get into these deep metaphysical questions about what real thinking or real understanding is, but I do want to maybe make it plausible that what these systems are doing is something close to a form of thinking or a form of understanding. And it's important for us to understand this in order to get a clear sense of what role they might play in various social endeavors. So maybe one can begin by, there's constantly now, it seems, headline grabbing kind of revelations about the capabilities of artificial intelligence. Here are just a few of them from this year, some of them quite recent. There was recently a paper that captured quite a lot of attention, that AI had been used to design a variety of bacteriophages. These are viruses that can be used to attack bacteria. And these are synthetic viruses that are generated by AI. So AI came up with the genetic sequences for these viruses. And the idea, at least, the hope is that one could use them then to attack bacteria that lead to disease or other pathogens, right? So this is one example of AI being used in scientific practice. Many people might have also heard about, in a more creative endeavor, the fact that the Commonwealth Short Story Prize recently went to a story, The Serpent in the Grove, earlier this year, that now people believe was probably generated by AI. And so it managed to convince the judges of this prize that it's worth the prize. So you also have significant advances in mathematics. This is a sketch of a recent mathematical problem that was solved by AI. It's a mathematical problem dating back to the 1940s. This mathematician Paul Erdős suggested this idea that, look, so the question he asked is, if you have a number of points on a plane, how many of them, how can you arrange them so that the maximum number of points are just the exact same distance from each other? You can think of it that way, right? Roughly. And so he was trying to say, okay, what are the maximum number of connections between these points that would be exactly the same length, the same distance from each other? That's the details of the problem don't matter. The point is, Paul Erdős, who was one of the most influential, prolific mathematicians of the last century, came up with a conjecture, a certain formula for calculating the number of connections. And until now, the assumption was that that conjecture is correct. AI recently proved that it's not, that Erdős was wrong, that there's actually a higher number of possible connections than Erdős suspected. Right? And so this is considered a major mathematical result that was, to a large extent, discovered by AI. Another very recent thing that I think was in the news quite a bit was AI models like OpenAI, in the process of their OpenAI trying to evaluate these models. So OpenAI was trying to evaluate whether they'd be able to pass certain benchmarking tests. And apparently, this is the news report at least, what AI decided to do is, instead of trying to, it figured the best way to pass these tests was not to solve the problems, but to hack into a database where the solutions of the problem were held. So this is a Hugging Face database which has solutions for various problems that are presented to AI. And OpenAI apparently spontaneously, these agents, AI agents, decided to hack into this database to extract the solutions as the simplest way of coming up with the solutions. And finally, in journalism, which is perhaps of special interest to all of you, this year's Pulitzer Prize winners, to take one example of use of AI in journalism, 1/3 of them, 5 out of 15 of the winners, had significant AI use as part of their reporting. This is not like using AI to write the reports, but using AI for various parts of the investigation itself, to scan through data, to present data in a form that's searchable, various different uses, right? And so this is 33.3% of the Pulitzer Prizes involve the use of AI. So the point here is that, look, when one hears more and more of these things, it becomes harder and harder to reconcile this with this conception of AI as merely mimicking its training data, as merely being a stochastic parrot. And it kind of produces this temptation to think of it as this maybe kind of intelligence that one might think of as either malign or benevolent or neither, or however one wants to think about it, but something that is thinking about things in ways that are unexpected, right? Instead of, it's coming up with strategies like cheating, which human beings come up with, but one might not expect, right, a rule-following system to come up with. And so I think the question about, well, how exactly do we characterize what is going on in AI? So I think that's an important question to get at least a sense of. My aim here is not going to be to give you a kind of complete idea of what AI is doing, but to hopefully give you an intuitive sense of what's going on under the hood with these modern AI systems. I should also mention, just for balance, that even though you have all these like very attention-getting successes of AI models, especially involving all these, and you often hear them as part of the marketing of these giant corporations that are trying to sell AI to you, a lot of our current information suggests that when AI is actually deployed in actual work contexts, it's not all that productive, right? This is the Apex Agents benchmark, which is a recent kind of benchmarking test that tried to deploy AI agents in various professional contexts and kind of measuring the success of it in the actual real world context rather than some artificial lab context. And it turns out that even the best performances are not very great. So it's, the best performance here in investment banking analyst was like 27% success, which is not perhaps what we're looking for. I should say that this is still improving. So the best performance last year was something like 5%. Now it's up to 25%. So perhaps in the future things could change. All right, so let's get back to this question. What exactly is going on with AI? I think a lot of us became familiar with artificial intelligence or started thinking about it once ChatGPT came into the picture, which was in 2022. This was the first kind of powerful AI chatbot that was made publicly available. But really, the major inflection point in artificial intelligence happened 10 years before this. ChatGPT was not the major advance. The major advance happened in 2012 with the development of a system called AlexNet. AlexNet was a system that was used to recognize images. So you have an image, it categorizes it as a particular kind of image. And the mechanism used by AlexNet to do this, a mechanism called deep learning, underlies a lot of the advancements in artificial intelligence that we're currently familiar with. So really, 2012 was this major first success of this kind of deep learning mechanism. This was by a team that was led by a person named Geoffrey Hinton, who subsequently won the Nobel Prize in 2024 for his work on deep learning. So what is going on? What is this idea of deep learning that we see with AlexNet, and we also see in ChatGPT? In order to understand that, I think it's first useful to think about how people used to think about artificial intelligence before the 21st century. So for most of the 20th century, or most of the second half of the 20th century, from the 1950s onwards, people who were working on building artificial intelligence, their assumption was that the way one should build an artificial intelligence is by explicitly putting rules into a system, right? Telling the system what rules to follow. Right? So if we want a system that's able to conclude, in this example, whether or not a particular animal is warm-blooded or cold-blooded, then you have to start out by inputting certain facts. The animal is a cat, it's a mammal, and then you put in certain rules. If something is an animal, it's living. If something is a mammal, it's warm-blooded. Things like this, right? The kinds of rules that we might follow when we're explicitly, systematically thinking through something. And so the thought was that this is how AI will be built, by building systems into which we pack in a lot of rules about how thinking should work. And this was a kind of strategy that was pursued for a long time, and it had some significant successes. One of the major successes of this symbolic AI, so this kind of AI is called symbolic AI, one of the major successes happened in 1997 when the world chess champion at the time, Garry Kasparov, played chess against a artificial intelligence system called Deep Blue that was built by IBM. And Deep Blue beat Garry Kasparov. And this was the first case of an artificial intelligence beating the best chess player in the world at the time. And this attracted a lot of attention. And Deep Blue was the kind of system I'm just talking about. A system that whose advantage over human beings came from a couple of things. First, it just was able to search through a lot more moves than a human being can think about, right? A human being maybe looks at a chessboard and thinks about 5, 10, maybe if you're really good, possible moves, and calculates the advantage that those moves will give you. Deep Blue was able to calculate a far greater number of possible moves and what their consequences will be. And then the programmers had explicitly also put in some rules that would tell it which kinds of moves to focus on and which ones not to focus on. So it was all based on the rules that were programmed in and just the computational ability to look at many, many different possibilities. Now, at the time, there was another game, which is called Go, which is another strategy board game, which people thought, look, this kind, AIs might be able to beat the best chess player, but AI will never be able to beat the best Go player. Why? Because Go is simply combinatorially much more complex than chess is. Right? There are many more possible moves at every stage. And so the advantage of searching for possible moves becomes less relevant because you simply couldn't build a system powerful enough to search as deeply as Deep Blue was doing for Go. And that was kind of the expected idea at the time, that chess might be a game where AI can beat people at, but Go, at least in the near future, is not going to be one of those. But then this should not be 1997. This is, I think, 2016 or 2017, something like that. Around 20 years later, the best Go player in the world, Lee Sedol, lost to an artificial intelligence called AlphaGo. There's actually a documentary on Netflix about this, which is quite interesting, called AlphaGo. But what was really interesting about this is that the way AlphaGo ended up beating Lee Sedol was not because it had these kind of pre-programmed rules. It was not a symbolic AI system. AlphaGo, in some sense, learned the game from scratch. It wasn't pre-programmed with rules and told how to play it. It learned the game from scratch. And it improved by playing against itself millions and millions of times. So it played games against itself, learned strategies, and then came up with strategies that were able to beat the best player. So what happened here was not symbolic AI. Right? It's not telling the machine what kinds of rules to follow. It's the machine coming up with its own rules for what is a good move and what is not a good move. Right? And this is the big phase transition, the big transition in how one thinks about AI. Moving from a framework where you put in the initial data and you put in the rules into an AI system and you get an answer in response, to a new framework where you start out by putting in data and then you give it the answers that you're looking for. So you tell it what, okay, you won this game, you lost this game. So you start out by training it on the answers. So you let it play a game, you tell it whether it won or lost, right? And gradually, based on that, it comes up with its own rules. So the rules are what are produced by the system. So the system is now coming up with the rules for how to think about the particular domain that we're dealing with, rather than those rules being pre-programmed into it, right? This is the transition from symbolic AI to deep learning AI, or machine learning, which is a more broader umbrella term for deep learning, right? Okay, so how exactly does this work? What exactly is happening here? In these deep learning systems are what are often called neural networks. Now, the term neural network is a little bit misleading because it suggests some kind of deep analogy with our brain, which I think one should resist drawing a very deep analogy with the brain. But the idea of the way neural networks work is you can think that there's multiple layers. And each layer is made up of neurons. These dots are neurons. And each neuron in each layer is connected to neurons in subsequent layers. And so you can see these neurons as these circles, and then the connections are the arrows between the neurons. And these different connections have different weights. So basically the idea is a neuron can become activated, can fire up, and if it fires up, the neurons that it's connected to will also fire up, especially if the weight of the connections is strong. And so you can start out with patterns in your initial system of layers, that are initial set of neurons, that are translated to other patterns in your next layer, other patterns in your next layer, and so on, through this process of neurons in one layer activating neurons in the other layer. Right? So you have these patterns being transmitted and gradually transformed as they move from layer to layer so you start out with a pattern representing your input and you get an output. Right? So in the case of AlphaGo, the initial pattern might be the state of a Go board, and then it undergoes a bunch of transformations until it gets to a decision about what move to make. And so if there's like 200 possible moves, it will rank all the possible moves by how likely it is to produce a victory. Right? So essentially what this deep learning system is doing is transforming one representation gradually into another representation. So you start out with a representation of the game board, and you end up with a representation of what we should be doing, what move I should be making or something, right? And in between, all these in-between layers are kind of doing this work of transformation. And this is where like I said when I began, something like thinking is taking place in these hidden layers between the input and the output. So what exactly is going on here? So I think it's useful, instead of thinking of the individual neurons, to just think of these layers as standing between an input and an output. Here's an example where, let's say we're trying to create an artificial intelligence system whose job is to interpret handwriting. Right? If we have, let's say, you write down a number with your hand, different people have different handwriting. We want the artificial intelligence system to be reliably able to read the handwriting, say what number it is, right? So if someone writes a 4 like this, the final output should be a 4. Yeah. And this was the kind of problem that early deep learning systems were aimed at solving. And so the idea, the thought is this. What does it take to recognize this as a 4? Well, there's certain structure in this that seems kind of 4-like. And the structure has to do with the way the lines are arranged, the way the edges are, where the edges are, what the angles of the lines are. All of these are relevant features of our initial input that would tell us it's a 4. Right? So some of the features of this input are relevant to saying that it's a 4. Other features might not be relevant. The fact that the background is black, that's not a relevant feature, right? You could have someone write a 4 on a black background. You could have someone write it on a white background. That is not a relevant feature. But the particular angle, the fact that you have a line crossing here, that might be a relevant feature, right? So what the AI has to learn, the rules the AI has to learn, is extracting the relevant features from whatever it is looking at, whatever input it's looking at, right? And so the transformation that has to happen here is a transformation that highlights the relevant features and suppresses the features that are not relevant. Right? Those are the transformations that take place. This is a process called feature extraction, getting features out of the initial input representation that you have. Here's an example of a transformation that might extract certain features. This is an edge detection transformation. So here's a picture of the Taj Mahal. Right? One transformation, here's an example of a transformation that highlights the edges, that removes all the color information, but highlights the edges of the image. Right? So this is moving from one representation to another representation of the data. And this representation might make it easier to recognize the image because it pulls out those features that might be most relevant to recognizing the image. Right? So that's kind of the heuristic thought behind what is going on in these deep learning systems. The transformation of your input into representations that highlight features that are relevant to whatever task the system is supposed to perform. Yeah. Here's a kind of sketch of how it might work with the system, the 4, where you start out with the 4, and then you might have different filters applied to the 4. Some of those, these filters look for lines and angles at different places. And we find that this filter is able to pick up the most lines and angles. And so this one will be the one that is activated most in this layer, that will lead to another one being activated most in the next layer, and so on. So as each layer goes on, we end up with representations that are more and more abstract, until we go from a visual representation like this to a completely abstract representation, just a 4, a single neuron lighting up as being 4, or something like this, right? That's kind of a sketch of the process that's going on. Of course, there's a lot more that could be said here. Here's another way of thinking about what's going on, is the earlier layers of a neural network, they pick up on very basic features. Features like the kinds of lines that, so if you have an image of a cat and you want to recognize it as a cat, the early layers will pick up on very basic features, lines, curves, things like that. It'll highlight those. Later layers will group them together into more abstract and more informative features, like, okay, there's an eye here, there's a nose, there's an ear, something like this, right? That is formed by grouping together these early features. And then if enough of those abstract features are cat-like, the final representation will be that this is a cat. So you have increasing abstraction of the representation, starting from just the basic visual features of the image to more collective ideas about what's going on. This is what the neural networks are doing, what deep learning systems are doing. This is just another sketch of this from a paper where you have an input, you have multiple layers that perform various functions. The exact nature of those functions, it doesn't matter for now, and then you get the neuron corresponding to cat is the one that is excited the most, not the one corresponding to dog, pig, horse, or whatever. Yep. So that's deep learning, very quickly, very briefly. A lot more to be said here, but I'd be happy to talk about it if anyone is interested in further details. But now, one question that arises is how does this, so I said the point is that the rules for how one representation is transformed into another are not programmed into the neural network. The neural network learns those rules itself. Right? This is how it differs from symbolic AI. We are not telling it that, okay, these are the features to look for to find a cat. We're just telling it, giving it a picture of a cat and saying this is the cat. And then the neural network has to figure out what features make it a cat. It has to come up with the rules itself. Right? And this is the way, and so here is, so essentially what happens, you have an input and then you have a prediction. So the input is, let's say, a picture of the cat. The prediction is that this is a picture of a cat. There's a bunch of layers of transformation that go on, a bunch of representations. Each of those representations, each of those layers is connected to the previous layer, and the connections have various weights. It's the weight of those connections that carries the rules about how one representation is transformed into another, right? The weights of the connections between each layers. And so those are the things that the neural network has to keep adjusting to come up with its final set of rules about, what I should do to figure out whether this is a cat or a dog or a horse or a pig or whatever. And how does it do this? It does this simply by by trial and error, by trying over and over to predict correctly, being told whether its prediction is correct or not. If its prediction is incorrect, it modifies the weight somewhat in the direction suggested by the way in which it was incorrect, until it finally comes up with a stable set of weights where it is able to predict things more or less accurately. So that's what's going on. The rules are being developed by the system through a kind of process of trial and error, through a process of trading, where it's not being told what rules to follow, it's simply being told whether it got things right or wrong. And every time it says, it realizes it's got things wrong, it modifies the weights associated with the different layers to move it slightly more towards being right. And ultimately, after many, many rounds, often sometimes millions of rounds of trading, it ends up with rules that work. And so the important point here, which is going to come back, is that the rules it ends up with might well be rules that we don't recognize. Right? We don't know what those rules are, and we might not, even if we knew what they are, we might not know why they work. Right? The rules that AlphaGo is using to play Go very effectively might not be the same as the kinds of rules that a champion Go player uses in their own mind to decide what move to play next. Yeah? And there's strong evidence that they aren't the same kind of rules, because many of the moves that AlphaGo makes are moves that even the best Go players in the world simply can't understand. They're like, this doesn't seem to make sense. Right? In fact, even in that game with Lee Sedol, there's one famous move which seemed completely inexplicable to all the humans watching. I think it's move 37 or something. It's there in the documentary. But it turned out, after the game was over, when people went back and analyzed it, that was the pivotal move that turned things around. And so part of the point is, when the system is coming up with its own rules, when we aren't putting in the rules that it follows to perform these tasks that we want it to, might be very different from the rules we follow when we're performing the same kinds of tasks. Right? It might be coming up with a very different way of doing the same thing that we do, or that we want it to do. This is an important thing to realize about these systems. So how does this image recognition stuff connect to the kind of AI that most of us are familiar with, which is large language models? Things like ChatGPT, things like Claude, and so on, where you can type in a question, it gives you an answer, something like this. Well, basically, it's the same kind of thing going on. It is a neural network, this deep learning system with many, many neurons, many, many layers. And the scales we're talking about here are huge. Right? So for example, the connections between different neurons these are of the scale of billions in the case of a large language model like ChatGPT or something, right? It's a huge number of connections, huge number of different weights that are being adjusted. So, but in the case of image recognition, we know what the input is. The input is an image, the output is some kind of classification of the image. This is a cat, or this is a dog. What is going on in the case of a large language model? Many of you might be familiar with this basic idea, which is what a large language model is, just a next token predictor. Right? Which is that you put in certain words, the dog sat on, and then it goes through the large language model, and what it's predicting is what is the highest probability word that should follow this. Right? What word makes most sense? Just like it's trying to predict in the case of a picture, what label makes most sense to apply to this picture. In the case of a string of text, it's trying to predict what makes most sense as the next possible word. So when these large language models are producing those answers, at every stage they're trying to figure out what is the most plausible word that should follow all the words that have come so far. And then it adds that on, and another one, and another one, and another one. Right? Using the same process we discussed earlier. And this is what has led people to this characterization as a stochastic parrot, which I'll come back to in a second. But the idea is here, yeah, the dog sat on, the is probably the next word that comes in, mat might be the next word that comes in. So it can fill in what seems like the most plausible follow-up for any partial sentence, and so it gradually builds sentences word by word or token by token. That's the most basic understanding of what a large language model is doing. Current LLMs are very complex. They have many more things going on under the hood, but the basic idea is still this. And this is what led Bender and others who she co-wrote with to characterize what is happening in these systems as stochastic parrots, right? So here's a passage from the paper where they introduce this concept. They say an LM, a language model, is a system for haphazardly stitching together sequences of linguistic forms it has observed in its vast training data, according to probabilistic information about how they combine, but without any reference to meaning, a stochastic parrot. Right? So what is the connection to a parrot here? Well, a parrot is able to produce seemingly meaningful language, but without anything going on in its head that corresponds to meaning construction. Right? And you might think what I just described is something similar. It's just making predictions based on, it's been fed all of these books, these texts, and in those texts, the tends to follow, the dog sat on tends to be followed by the, so just based on those patterns, it's saying the. It has no understanding of the concept of a dog, or the concept of a mat, or a concept of sitting. Right? This seems to be the difference between the way we think, the way we understand the world, and the way parrots do. Right? Parrots, even if they deploy language, they're not deploying it to some kind of conceptual understanding. I mean, this is questionable. There's some parrots that supposedly had some degree of conceptual understanding. There's a famous parrot called Alex, an African gray parrot, who could apparently understand at least basic concepts. But the general idea of a parrot is that it's just mimicking what it's heard before. It's not deploying a concept, right? So if you say to a parrot, you can train a parrot to maybe say, if you say the dog sat on the parrot will respond with mat. But it's responding only because it's heard that many times before, not because it has a kind of conception in its head of a dog and what it's doing, right? That's not what's going on. And so when we call AI stochastic parrots, we are applying a similar kind of idea to artificial intelligence, that there's no conceptual understanding underlying its linguistic behavior. Right? It's able to predict what to say, but that's not based on some kind of conceptual understanding of the way the world is. And the reason why I want to say this metaphor is maybe not the best metaphor is that it actually seems quite likely that there is conceptual understanding in the case of these large language models. Why? What does that mean? Why am I saying that? So here's, again, this is the basic picture I've presented so far. But think about what's going on in the case of image recognition. As I said, as we go layer to layer, you get more and more abstraction. So you start out with just the basic pixels in the image, then you get information about edges and colors, then maybe about shapes and textures, then maybe information about the parts like eyes, ears, and then finally you say it's a cat, right? That seems to be at least our best understanding of how these layers work and how they're related to each other. Similarly, at least one plausible way a language model might work, again, I'm not saying it definitely works this way, but one way it might work is that, again, you move to greater and greater abstraction. You start out with just words, syntactic words, you then go to grammar patterns, to phrases, entire phrases, and whether the phrases work. And then maybe at some stage in this process, concepts or ideas play a role. Why would we think that concepts and ideas might play a role? Well, here is an interesting thing that happens in a lot of these large language models, and a lot of deep learning models in general. There's this phenomenon called an information bottleneck. So, like I said, you have these layers of neurons. But you have this additional structure, which is that in the middle of the layers of neurons, you kind of have fewer neurons than you do at the two ends. And so what the system has to do as it's transferring information from layer to layer, creating newer and newer representations, is that here you can encode a lot of information in this layer. But in this layer, you have to rely on much smaller set of information. So what you have to do is you have to take all the information you start out with, throw out the stuff that seems less relevant to prediction, Keep only those features, those parts of your input data that seem like they're most relevant to predicting whatever you want to do. Right? Like I said, in the case of cats, it might be throwing out information about what the background looks like, keeping information about the shapes of certain parts of the anatomy, things like this. Right? In the case of language, it might be focusing in on certain aspects of what is being said, the dog rather than the on in the text or something like this. Yeah. And so these bottlenecks require, in the process of training, the AI system to, again, I'm going to use anthropomorphic language here, to make decisions about what information to discard, what information to keep. Right? And what this pushes is a particular way of making predictions. It turns out that when you have these information bottlenecks, when you have a limited amount of information, the best way to make predictions is to build models, simple models of the system that you're trying to understand. Right? This is what we do in science. How do we come up with predictions about what is going to happen in the solar system? We build a simple model. And that simple model involves focusing in on just those aspects that seem to matter, the masses of the planets, the distances between them and the sun, and leaving out all kinds of other information that we might have started out with, the positions of asteroids and so on. That's irrelevant. Leave that out. Right? So a decision about what information to keep in and what information to leave out is, in some sense, building a model of the world, a simplified understanding of the world that focuses in on those parts of the world that seem most salient, most important. But ultimately, in a sense, that is what the work that concepts do. What are concepts? Concepts are a way of encoding a lot of information in the world into simple representations, into simple models of the world. Think about what's going on here. So the early stuff you might think, if you just had to predict something like the cat sat on the, what comes next? Here you might imagine a system just blindly learning that after the cat sat on the next word that comes has to be mat. That's just blindly learning that through imitation without having to understand the concept of a cat and a mat. But as the sentences get more and more complex, as they become sentences that the systems are very unlikely to encounter in their training data, sentences exactly like that. That simple prediction strategy of looking up, okay, what is the most likely next move, that isn't going to work in general. But as we move to sentences like, she dropped the glass and it, I'm sure all of you could fill in the most likely next word. And it broke, yeah, something like this. Why were you able to fill that in? Not because you have a database of all the stuff you've read in the past, but because you have a concept of a glass and what happens when you drop it. Right? It's that conceptual understanding that lets you predict the next token, the next word. When you get even more complicated, the lawyer argued that her client was innocent because the security footage, here there might be various ways you can fill security footage, showed that he wasn't there or something like this, right? Or so there you also have to have a concept of what the different agents are, what they're doing, what their roles are, in order to be able to fill this out successfully. And when we move to really abstract sentences like the mathematical theorems that are being proved by AI systems, right? That seems to require, again, the idea that you can do this just through a kind of lookup table where it says, okay, here's half a sentence, here's the next word. Here's, if you have this other sentence, you have this next word. There simply isn't enough information or data in the AI model to be able to have that kind of extensive lookup table where every half sentence is paired with a sentence. Instead, the way prediction happens is the same way that all of you were able to predict what that broke would come after she dropped the glass and it. You have a world model in your head. And that world model allows you to say that, okay, this is what makes sense. She dropped the glass and it flew. Doesn't make sense giving a world model where we have an understanding of what a glass is. Now, are artificial intelligence systems building similar world models? It's not, for highly complex artificial intelligence systems, it's not clear because it's very difficult for us to understand what they're doing. But at least for certain simple deep learning systems, we are able to see them building these world models. This is from an experiment that was done in 2023. So this is another game, a game called Othello. And Othello is a game where you have two players who put white or black tiles down on a board, and if you're able to surround the tiles of your opponent, you can flip all the tiles that you surrounded. Basically, that's the idea. And the aim is to have more tiles of your color than the other color, right? Now, a deep learning system was built to play Othello. But importantly, the deep learning system was not given the structure of the board. It was just given letters corresponding to where each of the tiles is. So you can think of this as a grid, A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6. So you can say, okay, this is at D4, right? So D4 is the crossing. So the initial system was just given this. So it was just given strings like this, D4, E5, F6, E4. No further information about what these numbers mean. And then it was asked to give a new, add something to that sequence. And if it added something, it was told whether it was successful or not. So if it added something that would correspond, according to us, to a move that worked, we would just tell it, yes, you were successful. If it added something that didn't correspond to a move, it was told you were not successful. Again, no meaning conveyed to it beyond this success and lack of success. But the people who built this system, they use certain tools. For simple AI systems, it's possible to, in some sense, look into what is happening in those hidden layers in between. To do experiments to see what exactly are the representations that this AI is using in these hidden layers. And it turned out that the AI had built a representation of a board where it was doing this. There was actually a kind of visual representation of a board where you could, where certain neurons corresponded to certain squares and blocks being on the square. So just from this pure text, which for many of us, if we were just trained, from our childhood on like E4, B5, C6, what comes next? Or E7, B2, E1, what comes next? We might not think, okay, I have to think of this in terms of a game board where a particular game is being played with rules. But but that is what a conceptual understanding is, right? And that seems to be something that this system developed. It developed this representational structure of a game board and moves being made on the game board. Why? Because that turned out to be the most efficient way of making these predictions, of compressing information in order to make these predictions. And so simply thinking of AI as these predictive machines and thereby stochastic parrots, because all they're trying to do is predict, ignores the fact that often the most effective way to make predictions in the absence of substantial data or substantial data resources, computational resources, is to build simple conceptual representations. And so building conceptual representations, thinking through those conceptual representations, is something that, at least in these simple cases, we've seen AI doing. And once one looks at the capability of AI agents to be able to coherently fill out statements like this, I think it's a very strong possibility that even in these highly complex LLMs with their billions of parameters, weights, there is some kind of conceptual structure being embodied. Right? And so in that sense, this stochastic parrot metaphor is misleading because it makes us think of it as blind repetition rather than a form of conceptual understanding. Now, again, there's a metaphysical question about whether we should really call it understanding if it's not a conscious machine, but leaving that question aside, it is using concepts in a similar way to which we use concepts. But then, how is it that it gets things so obviously wrong in some cases? So this is something I did yesterday with Claude. This initially, when ChatGPT 5 came out, somebody noticed that you could do this with the word blueberry. Now, most of the AI has adapted to that. You can't do it with blueberry, but I came up with a fake word and did the same thing. So I asked it the question, how many A's are in the word banana berry? And then its immediate response is banana berry. Banana berry, there are 4 A's, right? Which hopefully you can all see is incorrect. There's only 3 A's in this word. And so then I said, that's wrong, count again. And then it said, let me recount carefully, that's 3 A's, not 4. So what's happening here? This is an example of an AI hallucination, something that you often read about in the news, where it just seems to get things wrong, confidently wrong. It doesn't say, I don't know, it just gives you a wrong answer. Yeah. How is it that these AI systems that are able, I mean, not this exact system, but systems slightly more advanced than this, are able to prove mathematical theorems that haven't been proved for 70 years, but yet they're not able to count the number of A's in a word? Like, what is going on here? Right? And maybe that kind of should reduce our confidence that there's a kind of genuine conceptual understanding, that really it's just spitting out what it thinks people want to hear, and because of that it gets things wrong. And I think the answer here is no, that's not exactly what's happening, right? In fact, I asked it what's happening, and it gave a kind of explanation, which you can look at. I'm not going to go into the details here, but I think the broad idea, again, this is not fully what it's saying, but this is partly my interpretation based on my understanding of what's going on, is that, look, AI systems form concepts, but they form concepts in ways that are very different from the way we form concepts. Right? When we learn to read letter by letter. Letters are kind of salient for us in the process of reading. Right? When you teach children to read, you first teach them the alphabet, and then how to put together sounds in the alphabet. And so letters are salient units for us. And so it's very easy for us to think in terms of letters. Right? It's very easy for us to answer the question, how many A's are there in banana berry? Because we can very easily separate it out into letters. If I asked you how many 30-degree angles there are in the word banana berry as printed there, you wouldn't be able to answer it as easily because those are not salient, important units for us. AI learns very differently. It learns concepts not through the same process of learning to read letter by letter, but through figuring out what chunks of information are going to be most relevant for prediction. And in general, usually, breaking up words into the individual letters is not very useful for prediction, for most of the tasks we use AI for. And so that ends up being something that AI is particularly bad at. AI doesn't build just concepts that are generally applicable no matter what the situation is. AI builds a conceptual scheme that is best fitted for the kinds of tasks it is trained on, right? And so its concepts are going to be geared towards the kinds of predictive tasks it is trained on. And the predictive tasks it is usually trained on are predicting the next word in text, which doesn't involve breaking up words into individual letters and counting those letters. So the point here is simply that hallucinations of this type, at least, are just indications of testing conceptual prowess on AIs where they have not had to build that conceptual prowess, build that kind of conceptual scheme. There's another kind of error that AIs make that I think is also instructive. And this is something called adversarial examples. So this is something you can do with AIs where take this picture, you give it to an AI that recognizes images, the AI classifies it as a pig. Then you add some random noise to the picture, it's very small random noise, so that the picture to us looks almost exactly the same. It doesn't look very different. So the pixels of the picture have been altered very slightly, but to us it still looks like almost exactly the same. You now show this to the same AI, say, what is it? It says it's an airliner instead of a pig, right? So what seems like an imperceptible visual change has made the AI completely misclassify this picture. What's going on there? Isn't that also an example of not really understanding, not having kind of the right sorts of concepts? And you can do this also with text, it's not just with images. I won't go into the details of that, but this is more generalizable than just with images. So these adversarial examples are cases where changes to inputs that we think are completely irrelevant end up changing how AI identifies the image. So think about what I said earlier. What is the AI doing? It's trying to extract features that it thinks are most relevant to recognizing this as a pig. And this might suggest it's extracting the wrong features because now this should still be recognized as a pig. Why is it being recognized as an airliner? Now what I want to suggest here is that when we actually think about what's going on here, and there's experimental evidence backing this up, this is not a mistake in the ordinary sense. Why is it not a mistake? Well, here's an interesting experiment that was performed by some scientists in 2019. So what they did is they first took a training image that the AI could recognize, like a dog. Then they performed this transformation where they added some random noise to it so that to us it looks the same, but the AI now recognizes it as a cat. So the AI now classifies this as a cat, even though we can see that it's a dog. Yeah? But here's the next interesting step. They took these misclassified images and they trained a new AI only on these images. So they told the new AI, this is a cat. And they maybe took another thing that looked like a dog but was actually a cat and said, this is a cat. And this new AI that was only trained on these mislabeled images actually got better at identifying cats. What does that suggest? That suggests that there was actually some information in here about how to identify cats that the AI was picking up. Otherwise, training on these images should have left the AI being useless at recognizing cats. It should have recognized dogs as cats. But it was recognizing cats as cats. It was learning to actually identify cats, even though it was never shown a picture that we would recognize as a cat. It was only shown these pictures that we would recognize as something else. Why? What's going on here? Why is it able to learn from this kind of thing? Well, plausibly what's happening is that there is a lot going on in this picture that we don't see. Right? Our sensory abilities are also limited. These two pictures look exactly the same to us, but they're not the same. And the random noise that's added to make it seem like a cat, that actually does have features that are in some sense typical of pictures of cats. Otherwise, it couldn't use those features to then learn how to recognize cats. So there's more to what's going on in the world than we can see. Right? That we pick up on certain features, but there's probably all kinds of features out there that we don't pick up on, that we don't recognize. And there is evidence that the AI is picking up on some of those features. Otherwise, how can it reliably learn to recognize cats by being trained on this? There must be something in there that allows it to recognize cats eventually. But it's not a feature that we can see. Right? So the point here is, even this error is an indication. It's an indication not of AI just randomly getting things wrong. It's an indication of AI not having the same conceptual architecture as us. Like we said, AI doesn't follow the same rules we do. It comes up with its own rules. And its rules are maximized for predictive success. Right? And so when we create an artificial image that to us looks like a dog, but we've added some random noise, so there'd never be a real life dog that looks like that, because that random noise is artificially added. The AI finds in that new picture features that are cat-like. We can't see those features. But the fact that those features can then be used to predict what a cat looks like suggests that there are real features in there that are cat-like. Right? It's just that the features that the AI is picking up are just not the same features we're picking up. So this is evidence of conceptual learning, but concepts that are misaligned from ours. Concepts that don't have the same structure as our concepts. Picking up features that are not salient for us, ignoring features maybe that are salient for us. Right? We are particular kind of beings with particular cognitive limitations, particular limitations in what we can see. The features of the world we pick up on is a small subset of the features that are out there in the world. And there's no reason to think that another rule-governed conceptual system will end up picking up on the exact same features as we do. And so this is at the end. I'll just end here. And so this, I think, is the real challenge that we need to contend with, and one that is kind of obscured by this characterization of AI as this unthinking, mimicking machine. I think one of the deep challenges of the increasing penetration of artificial intelligence into various aspects of our lives is not that this is an unintelligent or unthinking system, but that it is, in some sense, an alien intelligence, an alien form of thinking, right? One whose conceptual structure is fundamentally different from our own, because it's trained in a very different way, it's optimized for very different tasks than our body is meant to perform. Right? And so even though it might produce outputs that seem to us to make sense, and so we might seem like we can understand what's going on, it's making those predictions, it's identifying things as cats by looking at features that are not what we would consider to be features of cats. It has a very different conceptual structure. It's not that it doesn't have concepts. It just has concepts that are fundamentally misaligned from us. We're looking at the world through different filters. And so this problem is, I think, what we, so when like I said at the beginning, my work focuses on AI, the use of AI in science. And this is one central problem I'm concerned with, which is that one of the goals of scientific inquiry is understanding the world. And understanding the world requires being able to map on what we see in the world onto our conceptual structure. But if scientific work is being done by these alien systems that have completely disjoint conceptual schemes, then at most we have an illusion of understanding. You're producing these models which seem to be using the same concepts we're using. But those concepts are not actually the same. Just like the concept of cat the AI is using is not the same as ours. And I think this extends further to something that I'm sure all of you are concerned with, which is the use of AI in the media, to use the kinds of use we saw in the cases with the Pulitzer Prize, right? Using it to analyze huge amounts of data, to analyze images, and so on, geospatial images. Ultimately, science, journalism, a lot of these enterprises, part of their goal, I would say their central goal, is to create, to make the world more transparent to us. Right? To create a sense of understanding, to understand what is going on beyond what is immediately visible to us. The worry about AI is that once AI starts becoming the way the world is analyzed, the world becomes more and more opaque to us because we have to contend with this alien set of concepts that is not our own. I'll leave it at that. So yeah, I think I'm just about, yeah.
Hello sir, my name is Lavanya. My question is related to, can blockchain prevent AI generated fake news and deep fake news from spreading in the digital world today?
Can blockchain, so blockchain is at least one way of verifying. I don't know if it can deal with every single problem associated with AI generated news, right? And so the blockchain is essentially a verification algorithm or a verification method. And can it deal with every single problem of fake news? I don't think so, right? And so all the blockchain does is so it requires you to, in some sense, whatever information you're adding into the public store of information, it requires you to be able to show that you've generated that information in the right sort of way, right? You have a kind of function showing that you've generated that information in the right sort of way rather than using some tool that isn't. And then the blockchain verifies that this information was generated in the right sort of way. I think that's far too limited an algorithm to account for the various ways in which we collect information about the world and the ways we spread information about the world, right? So it's not clear to me that that's going to be a general
Also, how is it connected
solution
with the journalism field using of the blockchain too? If you could explain.
Honestly, this is something that maybe someone here would be more equipped to talk about than me. I'm not sure if it's already in use in journalism or not. I mean, the place where blockchain is most used, obviously, is in the context of cryptocurrencies, right?
Yes.
Where the aim is to verify transactions. And I assume that what you're suggesting is that instead of using it to verify transactions, you use it to verify the means by which information is added into the public store of information. I don't know if that's something that's already happening in journalism. I think, there's all kinds of worries about that. Blockchain is computationally quite intensive because you need to reproduce the same chain of information in every computer that's part of the network. So I don't know if this is actually a kind of general purpose solution that's going to work. But yeah, it's not an area where I'm super well versed. Yeah.
Thank you, sir.
Yeah.
Anybody?
Good morning. Just a quick question. You've spoken about conceptual structure being the difference between AI and us. And I just want to understand how then should we interrogate AI systems when bias is not like the obvious answer, but most of it is like embedded in the data that the models are trained on.
Yeah, so this is a deep and ultimately unanswered question, that how do we interrogate these systems? So one of the big kind of areas of inquiry in AI currently is how to make AI systems explainable or transparent to us, right? How to make AI systems interpretable. And it's turning out to be a very large challenge, I think partly for the kinds of reasons that I've talked about. We have techniques for making simple AI systems, like the kind of board game system I talked about, ways of making them interpretable. But for us to be able to look into these highly complex AIs with millions of neurons, billions of connections, and be able to extract the conceptual structure that is being used, that is something that, at least right now, is beyond our ability to understand how to do that. So what people end up doing is trying to reconstruct what the AI tried to do. So in some sense, get the AI to come up with a story of what it did. So this is what's often called chain of thought methods, where the AI tries to reconstruct its method of thinking. But the important thing to realize about chain of thought is that this is also an output the AI is producing, right? And the AI doesn't produce output maximized for truth. It produces output maximized for whatever task it's meant to. So in this case, maybe satisfying human beings and making them think this is plausible. So the chain of thought it produces, there's no guarantee that that's actually what happened within the system. It's just a reconstruction that will be satisfying to a human being who'd be looking at it, right? So yeah, this is a difficult question. I don't think there's any easy answer to it right now. Yeah.
Hello, sir. I'm Laksa Upreti. And well, the topic has been today of digital wisdom. So I would like your wisdom on this discussion, that you talk about hallucination. when it comes to AI. And you even said that eventually the model recognized the difference between a cat and a dog. So do you think that over the decades, there might be a possibility that AI understands our cognition and then its reasoning matches ours?
So I certainly think that the rate of hallucinations in AI is going to go down because a lot of effort is being made to ensure that, and it has been going down quite rapidly. But I don't necessarily think there's any like special pressure leading to the alignment of AI concepts with our own, right? Because AI continues to be used for predictive tasks which humans are not good at, right? And, that's the main thing we use it for. And often the way to become better than humans at predicting something is to pick up on features that humans don't pick up on. Right, to focus on things that humans don't focus on, which means coming up with concepts that are different from human concepts. So as long as the kind of unique selling point of AI is in its predictive advantage over human beings, in order for that predictive advantage to be sustained, in some sense it's because of the conceptual gap between our conceptual structure. Obviously part of it is just the computational power of these AI systems, but a lot of it is also the fact, even the mathematical example I pointed out at the beginning, the unit distance problem, the Erdish problem. It turns out the reason AI was able to come up with a proof that humans were not able to come up with is that the AI used a completely different representation of numbers, a very non-standard representation than humans have been using until then. So this is another sign of AI being able to solve the problem just because they carve up conceptual space in a very different way than we do. And I don't see any special pressure that's going to lead that to be less significant in the future. Yeah.
Sir, I had two questions actually. Sir, first you told us about you told us about the way AI thinks and how you are looking into how it comes to its conclusions. Sir, what exactly is the process? Do we go layer by layer? Can we see its thought process? Is that a possibility?
No, so we can't. So, I mean, what you can see is you can see which particular, I mean, to some extent at least, which particular neurons in a layer are being activated, to what extent they're being activated. In smaller AI systems, that's easier to do it highly. But then translating that into what representation it's using is often not possible. Right? It's as if someone took a brain scan and saw which neurons in your brain are lighting up, to be able to translate that into what you're thinking about or what you're conceptualizing, right? So simply knowing what neurons are being activated in a layer doesn't tell us how a representation is being encoded in that pattern of neurons, right? So simply so that's what we want to track is the representations and how they're changing. And that can often, I mean, we don't have generically good strategies for doing that as of now, yeah.
Sir, in the scientific world, you said that AI could possibly give us scientific conclusions to things and hypotheses basically, but we won't know how it arrived at those. So, sir, is that something that is happening? Are we taking scientific hypotheses given by AI and then trying to prove it? Is that a plausible way for science to go?
It might, but so my worry about that is I think the concepts that are most optimized for prediction and the concepts that are most optimized for understanding or explaining the world might not be the same concepts. This is my worry, right? So if we follow a path where we first allow AI to build predictive models, then we try to understand those predictive models, we are kind of chaining ourselves to the conceptual structure that the AI has come up with, which is a conceptual structure aimed towards predictive success, right? Whereas historically, the way science has happened is that the concepts that scientists develop are concepts that develop gradually through a process of coming to an understanding of the world, right? Like, for example, when scientists came up with the concept of force, the idea was not here's a concept that is best predictively. It's that here's a concept that gives us a model that helps us understand the world, and then we build predictions on that. But the idea of first building a predictive model based on whatever concepts might be best suited for that, then extracting understanding from that it seems unclear to me, but that will be a strategy that works all the time, right? Because the concepts might not be the same, the ones that are suited for understanding and suited for prediction. Yeah.
So the last question. Yeah.
Sir, Devarup this side. So my question is more of an economic one, where we are seeing AI market booming almost. There is about 36% of investment in AI market in US. but many authorities like Sam Altman and even the IMF is saying there is a risk of AI market being a bubble, economic bubble. So what's your view on that?
Yeah, look, I have nothing more than a layperson's view on this, so economics is not my area. I think there are some signs of the AI market being a bubble. I think the amount of growth in AI investment is not so far justified by what the industry is producing in terms of productivity gains. I think that is clear. A lot of it is speculation about future productivity gains that AI will get us. You already had the recent drop in the Korean stock market, which was buoyed by AI-based investment. But the Korean stock market, even after that drop, is far above where it was a few years ago. So yeah, I guess I don't have a very kind of expert level answer to this question. All I can say, it seems to me to show signs of being a bubble in the sense that a lot of it is speculation about future productivity gains. I don't think there's any guarantee that the way AI is being used, as I said at the beginning, as I showed at the beginning, when AI is actually deployed in real world work environments, the productivity tends to be not as good as one might hope in order for AI to be able to perform a lot of these tasks that would justify the kind of investment it has. But another thing about AI is that it's a technology that is rapidly changing. And so if that rate of change continues, which also there's questions about whether it might be saturated on the rate of change, then maybe some of the speculation will bear out. I don't know. So this is a question for an economist who's worked on this, not me. Yeah.
Thank you very much, Tarun. Fascinating lecture.
Thanks a lot.
Thank you
everyone.
very much indeed.